Hello, I am Dipankar Bhattacharya. I work at Inter-University Center for Astronomy and Astrophysics in Pune. We will talk about compact stars in this module. There will be 3 lectures. We will divide the subject in these 3 lectures. Let us start by a quick introduction to what we mean by compact stars. You have so far heard about regular stars and their evolution in other modules. Compact stars are end states of stellar evolution. Normal stars shine by generating energy in their centers by nuclear fusion. However, in compact stars, there is no internal nuclear energy generation. We of course see compact stars, so that means there is some radiation that is generated by them. But this radiation comes at the expense of either the stored internal energy, for example, the star may be hot, so in which case you will get thermal energy which leaks out and the star cools, or it could be tapping its rotational energy through magnetic fields, and in some cases even the magnetic energy itself can be tapped to generate radiation from these stars. A whole section or the whole class of compact stars are seen in radiation generated by gravitational energy converted to radiation, which is released by matter falling onto the star from nearby medium. So, this could be either from another star, which is a binary companion, or diffuse gas which surrounds the compact star. As this gas falls onto this strongly gravitating objects, they release gravitational potential energy that goes into heating this material, and this hot material then radiates. So, this is how we are able to see compact stars, although they do not have a inner nuclear energy generation. So, what are the stars or what are the objects which fall in this class? White dwarfs are the least dense of this compact star family. They are roughly like a mass of the sun squeezed into the size of the earth. So, that would tell you what one means by compact. So, densities are very high. So, masses of white dwarfs are somewhere between small fraction of a solar mass to a maximum of about 1.4 times the mass of the sun. The radii are a few thousand kilometers, and they are seen in various wavebands including optical, ultraviolet, X-ray. They are seen as central stars of planetary nebulae, as well as they are seen as cataclysmic variables which are accreting white dwarfs. We will discuss these in more detail as we go along. The next denser class of compact objects are indeed extremely dense, where you squeeze the sun to within the size of a city more or less. The masses of these objects are about 1 to 2 times the mass of the sun. The radii are only of the order of 10 kilometers. They are observable to us in wave bands like radio to gamma rays. They are seen as pulsars, magnetas, X-ray binaries, and these objects are supported by nuclear forces within the star, because the density is such that they are as high as the density inside an atomic nucleus. By and large, as far as compact stars go, these two are the main families that one finds in nature. There has been hypothesis about other kinds of objects which might masquerade as similar compact stars, similar to neutron stars. They could be quark stars made entirely out of quarks, or hybrid stars, which is a mixture of quarks and neutron star matter. And there are wild speculations about other types of stars called boson stars as well. We will not discuss these exotic varieties in much detail. Our main discussion will confine to white dwarfs and neutron stars. And of course, neutron stars themselves have an upper limit of mass. If you try to create a compact object which is more massive than this neutron star upper mass limit, then what you create is a black hole. So, stellar mass black holes that we come across have masses a few times the mass of the sun, but stellar mass black holes are not the only type of black holes known in nature. Some black holes which we know, which reside in the centers of galaxies, could be many millions to billions of solar masses. So, there is actually no upper mass limit of black holes. However, black holes are not self luminous in themselves in any way. Black holes, the presence of black holes can however be inferred from the matter which falls into the black hole, and in the process of falling into it, they get hot and radiate, and this is called accretion powered activity. In the lectures on stellar structure, you would have come across the stellar equilibrium condition, which we refer to as hydrostatic equilibrium. The equation of hydrostatic equilibrium in full general relativity is what is shown here in the top line. It is the pressure gradient, negative pressure gradient, is balanced by this quantity on the right hand side. It is gravitational constant times mass within a radius r. Then there is this quantity 4 pi r cubed pressure at that radius r divided by c squared. Multiplied to this is the density at radius r. This is pressure at radius r divided by c squared, and in the denominator you have r squared multiplied by this Schwarzschild factor, which is 1 minus 2 g m by r c squared, where m again is the mass contained within radius r. Now, this is the full form of hydrostatic equilibrium equation in general relativity. This full form of equation becomes really relevant in the densest of objects like neutron stars or black holes, or objects of that high degree of compactness. For most other stars, including normal stars, a Newtonian approximation of this hydrostatic equilibrium suffices to describe the object, and what is written in the second line is the Newtonian approximation to this full hydrostatic equilibrium equation, which is much simpler, which is again the pressure gradient on the left hand side, that is balanced by the gravitational constant times the mass within radius r, density at radius r divided by r squared. And for most objects, normal stars, including white dwarfs, this is the form of the equation that we will mostly use. So, this is valid when the compactness, that is m over r, is very, very small. M is the mass included within radius r. So, m of r is the mass contained within radius r, so which is defined as integral from 0 to the radius r 4 pi r squared density at radius r dr. Now, given these two definitions, one would be able to solve for the structure of the star, provided we are able to substitute this with a relation between pressure and density. So, this supplementary equation, which is required to complete the system of equations to solve for the stellar structure, is called the equation of state, which expresses pressure in terms of density and perhaps other state variables of the material. And the more the number of state variables, the more the number of equations you have to add in the chain to make sure that the system of equations is closed. Given these equations, we can now solve for the equilibrium structure of the star. What kind of star it is actually is simply determined by what equation of state you provide. If the equation of state is such that the pressure is primarily given by the thermal pressure, that is, pressure is function of density and temperature, and the thermal motion of particles is the main cause of the pressure, then what you get out of this stellar equilibrium solution are normal stars. On the other hand, if the pressure happens to come from sources which are not thermal, then we get this new family of objects which are called compact stars. So, when we say pressures which do not come from thermal sources, what kind of other pressure sources could be there? The type of pressure that becomes very important in compact stars is called degeneracy pressure. The concept of degeneracy pressure is illustrated in these diagrams. Let us take electrons as the constituents of these stars. Now, electrons are elementary particles with half integral spin, with spin of h cross by 2. Now, such particles obey Fermi-Dirac statistics leading to Pauli's exclusion principle. Now, Pauli's exclusion principle states that if you define a quantum state, then you may at best put two particles of opposite spin in that one state. Now, here we are talking about electrons confined within a star. The electrons are free to move about within the star. So, the phase space of these electrons is a 6-dimensional space where there are 3 position coordinates and 3 momentum coordinates. Now, these 3 position coordinates and 3 momentum coordinates make up this 6-dimensional phase space, which can be split up into individual quantum states, each of volume h cubed. Now, each phase space cell in this phase space volume can then contain at most 2 electrons with opposite spin. So, now if you start with a certain volume where you place a certain number of electrons, and let us assume there is no thermal motion, we remove temperature completely, then the phase space of this system consists of a number of cells. Now, I have shown a one-dimensional representation of the phase space here. Let us take one coordinate x and the corresponding conjugate momentum p. So, this phase space now has these many cells, and when you start placing electrons, you start placing them from the smallest value of momentum, but once you have run out of cells, the next set of electrons you have to place in a set of levels where the momentum is somewhat higher, and the next set of electrons you will have to place in with even higher momentum, and so on. Now, assume that I make the density higher, that means I squeeze the position coordinate, keeping the number of electrons the same. Then as you can see, since the cell size in phase space remains the same, which is in 3 dimension it is h cubed, the only choice you have to populate the phase space now is by putting the electrons into higher and higher momentum states. So, therefore, once you have electrons confined within a certain volume, just by the virtue of that confinement, the electrons acquire a certain momentum. and once you have a momentum, that leads to pressure, and this is the source of degeneracy pressure. The smaller the volume, the higher is the momentum, or in other words, the larger the density, the higher is the momentum, and therefore, higher is the pressure. So, therefore, you get a pressure which is simply due to this Pauli's exclusion principle, and this degeneracy pressure rises as you squeeze the matter to higher and higher density. So, if you want to be a little bit more quantitative on this, let us look at this. Let the number of electrons per unit volume be NE, and the momentum up to which the states are filled, let that be Pf, where the subscript F refers to Fermi, and this momentum is called the Fermi momentum. So, the number of phase space cells in a 3-dimensional volume, in 3-dimensional momentum space, will be 4 pi by 3 Pf cubed, and let us take unit volume of configuration space. So, multiply this by 1. So, the phase space volume then becomes 4 pi by 3 Pf cubed times 1, and since the volume of each phase space cell is h cubed, we divide this 4 pi by 3 Pf cubed times 1 divided by h cubed. So, that is the number of phase space cells which are filled. Each of these phase space cells can take 2 electrons. So, 2 times the number of phase space cells, therefore, must be the number of electrons present in that unit volume, and let us call that Ne. So, then we have this relation between the Fermi momentum and the electron density. So, that is 4 pi by 3 Pf cubed by h cubed is Ne by 2. You can therefore rewrite this as Pf being equal to 3 by 8 pi to the power of 1/3 h Ne to the power of 1/3. So, this is the momentum that the electrons will achieve by virtue of being confined with a number density Ne. How do we find the pressure that will be caused by these electrons? That is simply obtained from the definition of pressure. The pressure is nothing but a momentum flux. So, if you take an unit area, then you look at how much is the total momentum crossing that unit area per unit time. So, let us take an unit area and let us wait for a unit amount of time. Since the electrons would have a speed v, then in this unit amount of time, this will sweep out a volume which is equal to v. Number of electrons present in that volume will be Ne times v, and each of these electrons, let us say it is carrying a momentum p, then Ne times v times p will be equal to the pressure. Now, from what we have described, it would be clear to you that this average momentum that an electron will carry in such a situation will be proportional to the Fermi momentum. The pressure therefore, is Ne times v times the Fermi momentum with a proportionality constant. Now, what is the velocity that we should use in this expression? Velocity is related to momentum. If the motion is non-relativistic, that is speeds are far less than the speed of light, then the velocity may simply be written as the momentum divided by the mass of the particle, so it is p by m e. So, then using this expression, we will have the pressure proportional to Ne times p again here and p, and each p is proportional to Ne to the power of 1/3. So, you will have Ne times Ne to the power of 1/3 times Ne to the power of 1/3. So, altogether you will have pressure proportional to Ne to the power of 5/3. This is as long as the speed is much less than the speed of light. However, as you keep going to higher and higher density, the Fermi momentum will keep increasing. As the Fermi momentum increases, the corresponding speed will also keep increasing. But can the speed increase indefinitely? No. When you go to very high densities, the speed will saturate at the speed of light, and when you reach that situation, in this expression, then instead of this v, you will just have to use the speed of light c, and then the dependence of pressure on density will lose one factor of n e to the power of 1/3, and you will get pressure as being proportional to n e to the power of 4/3. So, as the speed v approaches the speed of light. So, this is the form that we will have of the degeneracy pressure. We have discussed this in the context of electrons here, but any fundamental particle with half integral spin will behave in a similar manner. Some related concepts associated with this Fermi momentum P f, there is a Fermi energy which is E f, which in the full relativistic expression is expressed as square root of P f squared c squared plus m squared c 4. This Fermi energy will represent the highest energy electrons present in a 0 temperature system, which is degenerate with a Fermi momentum P f. The matter is actually termed degenerate if you define a temperature T f just dividing E f by the Boltzmann constant, if that happens to be much larger than the real temperature of the system at that point. So, if the material is much cooler than this Fermi temperature, then the source of pressure is primarily degeneracy pressure, and we call this matter as degenerate matter. So, let us look at the kind of stars that you can build with such degeneracy pressure. Let us start with electron degenerate systems, where the pressure is supported mainly by electron degenerate pressure. As we said, the pressure itself has an expression which is proportional to electron density to the power of 5/3 at low density, going over to electron density to the power of 4/3 at high density. In solving the hydrostatic equilibrium equation, we need relation between pressure and mass density, not pressure and electron density. So, we have to count for each electron present how much mass is present in the system, and that is counted in this expression which we have written here. Let us take for each electron, let there be mu e times the number of nucleons present in the system. So, nucleons will include protons and neutrons. For example, let us take hydrogen. For every electron, there is one proton present. So, in that case, mu e is equal to 1. On the other hand, if we go to helium and fully ionize it, we get 2 electrons and a helium nucleus. A helium nucleus contains 2 protons and 2 neutrons. So, we get 2 electrons and 4 nucleons, in which case mu e will be equal to 2. And if you go through the periodic table for all elements heavier than hydrogen, you will find mu e will remain more or less equal to 2. So, except for hydrogen, the value of mu e in white dwarfs will almost always be close to 2. So, therefore, if we now take the actual mass density and divide by mu e times the atomic mass unit, then you will immediately get the number density of electrons in the system. So, the previous expression where Ne appeared, we have here replaced Ne with rho divided by mu e m p. Now, this equation stands before us in a form which we can use to solve the hydrostatic equilibrium equation. So, this is our equation of state. So, this is in the non-relativistic extreme, and here we have rho by mu e m b to the power of 4/3 in the relativistic extreme, when speeds become close to speed of light, or Fermi energy becomes larger than the rest energy, or P f becomes larger than rest mass of the electron times c. Practically, that corresponds to the mass density being above about million grams per cubic centimeter. So, if the mass density is above that, the relativistic version of this equation of state is more relevant. Below that, non-relativistic version is more relevant. Now, with this electron degeneracy pressure, we have to now solve the hydrostatic equilibrium equation. Very roughly, we can rewrite the hydrostatic equilibrium equation in a very crude form, where we have the degeneracy pressure equaling g m to the power of 2/3 rho to the power of 4/3, where we have replaced the radius r that appeared in the equation as being proportional to m by rho to the power of 1/3. Here, as I said, this is a very crude relation, but it is very useful for looking at dependences. This will not give you exact numbers, but it will give you a good idea of the scaling relations and various dependences. On the left hand side, we can now replace the expressions for degeneracy pressure as we have quoted above, and then if we solve for it, there is rho here, there is rho there. You will find that for non-relativistic, you have this relation over here. So, you have radius proportional to mass to the power of minus 1/3, and this radius for this kind of system happens to be about 10,000 kilometers for mass of about 1 solar mass, which means the heavier the object, the smaller is its radius. This is contrary to our terrestrial experience. Object is heavier if the radius is larger. So, bigger objects are heavier, but in this case, because of the nature of the degeneracy pressure and gravity, the heavier objects supported by electron degeneracy pressure have smaller radii. So, that means as you keep on adding more and more mass, the object is going to get smaller and smaller. At some point, the density will increase so much that the relativistic version of the equation of state will become relevant. Now, if we use this relativistic version of the equation of state in this expression, then you will find that the density, radius and so on, they cancel out. You get a unique value of the mass. What is the meaning of this? That means that if you push the density to such high values that the entire star becomes relativistic, then it is only this mass that can be supported. Now, in the process of approaching it, you will have less density. So, you will have a smaller amount of mass, but once you have reached this mass, that is the limit. You cannot sustain any more mass against gravity by electron degeneracy pressure. So, this is called the limiting mass of these configurations, and also goes by the name Chandrasekhar mass, because he was the first to point this out. The value of this Chandrasekhar mass turns out to be around 5.76 mu e to the power of minus 2 solar mass, and as we will see presently, most of these white dwarfs are made up of elements that is helium or above, and therefore, mu e is roughly equal to 2. So, the value of this Chandrasekhar mass is about 1.44 times the mass of the sun. We can illustrate this process schematically in this diagram here. What I have plotted in blue is the electron degeneracy pressure. At low densities, the pressure rises as rho to the power of 5/3, and at high densities, the pressure flattens out with a smaller slope of rho to the power of 4/3. The horizontal axis here is logarithm of density, the vertical axis represents logarithm of pressure. Now, this degeneracy pressure has to balance this gravitational pressure, so called gravitational pressure, which is g m to the power of 2/3 rho to the power of 4/3. So, for any given value of mass, these are represented by these sloping white lines here. As you go to higher and higher masses, the constant in front increases. So, you go to lines which rise over here. Now, as you can see, let us start with a mass like this, the bottommost white line. This line intersects the blue line at this point. So, that represents an equilibrium. So, that equilibrium will have a density which you read off from this red line below, where it intersects the horizontal axis. Now, if you go to slightly higher mass, you go to this point in density, that means the density increases. So, that this is as we discussed, that the material becomes more and more dense as you increase the mass of the configuration, and the radius will also drop as r to the power of minus 1/3, and the radius will also drop as m to the power of minus 1/3 as you go to higher and higher masses. What happens if we keep increasing the mass? The slope of this line is 4/3 in this diagram, which is the same as the slope of this electron degeneracy pressure in the relativistic branch. So, as you keep increasing the mass, at this point this line has become tangent to this relativistic pressure. If you go to a higher mass, then you can see that there is absolutely no intersection of this white line with the blue line. So, therefore, the pressure represented by the blue line will not be able to make any equilibrium configuration by supporting this white line. So, therefore, that mass cannot be supported by electron degeneracy pressure. The maximum mass that can be supported is the one that becomes tangent to this line. So, that is your limiting mass or the Chandrasekhar mass. So, this is a rough description schematic, because we have just taken a crude approximation of the hydrostatic equilibrium equation to illustrate the main physics behind. To compute this correctly, of course, one has to take the full expression of the pressure into account. So, we do not take just the asymptotic versions at the non-relativistic and relativistic end, but take this complete expression which is written here, where the quantity x is momentum by MEC and is defined as this. We can then go for the solution of the full hydrostatic equilibrium equation, and we can plot the results with mass on the horizontal axis and radius on the vertical axis. Here the numbers are normalized to certain values, and this picture is taken from the original paper of Chandrasekhar, where he computed this for the first time and then showed that the mass radius relation has this form. In this low mass range, this shape is radius proportional to mass to the power of minus 1/3, that is this dotted line here. As the mass increases, the mass radius relation will deviate from that, and then as you go to more and more density, larger and larger part of the star will be covered by the relativistic core. So, now in shaded region here shows the fraction of the star that is covered by the relativistic core. At lower masses, that portion is very tiny. As you go to higher masses, that portion increases to cover almost the full star, and then finally, when that relativistic core covers the entire star, you reach this limiting mass, which is the same as what I mentioned before, which is 5.76 mu to the power minus 2 solar mass, which is about 1.44 solar mass for mu equal to 2. So, what have we learned so far? We have learned that these stars, which we now call white dwarfs, their stellar configurations supported against gravity by electron degeneracy pressure. There is no energy generation that happens in the interior of these white dwarfs. The typical radii are about 6,000 kilometers for about one solar mass white dwarf. Higher mass white dwarfs are more compact, are smaller in size, and then there is a limiting mass above which white dwarfs cannot exist, and this limiting mass is called Chandrasekhar limit, which is about 1.4 times the mass of the sun. Now, white dwarfs are often found inside what is called planetary nebulae. Here is a picture, real picture of a planetary nebula, which contains a bright dot inside, which is the white dwarf. This planetary nebula is a spherical distribution of gas, which is being illuminated by the hot radiation that is escaping from the surface of the white dwarf. Where did this come from? This is the reminiscent of the process of formation of a white dwarf, and this goes back to the evolution of the star that the white dwarf came from. A normal star has a structure where there is a nuclear fusion going on, but nuclear fusion does not cover the entire star. The nuclear fusion happens in a small fraction of the star, which is the core, typically about 10%. The rest of the star is too cool to undergo nuclear fusion. Now, in the central part, which is the core, which is indicated in red here, is consuming nuclear fuel. So, let us start, let us say, from a hydrogen star, and initially the star is burning hydrogen in the core. It is in this core region that hydrogen is getting converted to helium, and at some point the entire hydrogen will get consumed and the nuclear fuel will run out. And therefore, it is this core which is now ready to contract, collapse and form a more compact configuration. As it contracts, if the situation is right, it may ignite further stages of nuclear burning. So, helium may then burn into carbon, carbon may then burn into oxygen, neon, magnesium, which may then burn into silicon, which may then burn into iron. If all these stages of nuclear fusion are allowed by the process of evolution, which we will briefly discuss in a moment. But what will eventually form the compact collapsed star is the core in which the nuclear fuel has been exhausted. The rest of the star, which is the envelope, will in this process become distended and be expelled eventually. And what we are seeing here is the result of such a process, where the core has collapsed to give you this compact star called white dwarf, and the envelope has been expelled and it is expanded and now shines, being illuminated by the radiation from the white dwarf as the planetary nebula. I just mentioned that there are various stages of nuclear burning that can take place in the core of a star. the first stage of course, is from hydrogen to helium, which releases the maximum amount of energy per nucleon. What is plotted here is the nuclear binding energy curve. On the left hand side in the vertical axis is the nuclear binding energy, and on the horizontal axis is the atomic mass. So, now as you go from helium to the next burning stage, it forms carbon, which also releases significant amount of energy, and then all these subsequent burning stages are indicated here by the squares. Ultimately, you may burn all the way to produce iron in the core. However, beyond iron, the fusion process becomes endothermic. So, that means there will be no energy generated, no net energy generated going from iron to any heavier elements. So, natural process of fusion generating energy actually stops at iron peak elements, which is iron, cobalt, nickel, and that gives the end point of natural nuclear burning within stars. Will all stars proceed this full way to burning nuclear fuel to generate iron? Not so, and the degeneracy pressure has a main role to play in deciding that as well. And this is called degeneracy-limited nuclear burning. So, we will come back to this same diagram which we illustrated before. Again, we have log density in the horizontal axis, log pressure on the vertical axis, and we have this equilibrium condition where the central pressure is m to the power of 2/3, rho to the power of 4/3, which you have to balance by the pressure available within the star. If the star is held by thermal pressure, then for a given temperature, this pressure is proportional to just the density, power of density to the power of 1. You have these red lines that correspond to specific temperatures, and the pressure, central pressure corresponding to those specific temperatures. And these specific temperatures here we have mentioned the threshold temperature for burning for hydrogen, helium, carbon, and so forth. So, when a star is burning hydrogen, its central temperature is constant around this value. So, therefore, all configurations which are hydrogen burning will fall more or less on this line, and if there are different masses, then you can have the corresponding intersections of this g m to the power of 2/3 rho to the power of 4/3 line with this hydrogen burning temperature line, and those intersections will give you the equilibrium configurations of such objects. As you can see, as you go to higher mass, the curves here, this is the lowest mass, this is the highest mass. As you go from lower mass to higher mass, the intersection points move to lower density in these cases. So, the centers of more massive hydrogen burning stars are less dense, and it is so for any other burning stage as well. So, let us consider a star of mass like this. Initially, it was contracting before it became a hydrogen burning star. At this point, hydrogen ignites and the star will find a balance for a long time at this point, where hydrogen burning provides for the energy loss from the surface. Or at some point, hydrogen burning will stop because all the hydrogen in the core has run out, and the star will then proceed with further contraction along this line, which is a constant mass line, and if it reached this point, it would have ignited helium. However, if the mass is too small, before intersecting this line, it will intersect the blue line, and this blue line intersection will then provide a long standing support of the configuration by degeneracy pressure. So, the star does not need to contract anymore, and it does not need to get to this point at all. So, which means the life history of this star will end with hydrogen burning. It will not ignite helium at all. A more massive star can go through both hydrogen burning and helium burning, and even more massive star may go through other stages of nuclear burning. By the time you get to the most massive stars that can be supported by degeneracy pressure, you would have gone through all stages of nuclear burning. In any case, above this mass, you will not have degeneracy pressure support stopping you from further contraction anyway. So, depending on the initial mass of the star, the remnant white dwarf will have a different composition. The observed white dwarfs have a distribution of masses which is displayed in this diagram. We actually happen to find a peak around 0.6 solar mass, but there are of course masses on both sides of that going all the way up to about 1.4 solar mass. Because of the degeneracy limited nuclear burning which I just mentioned, if the white dwarf mass happens to be less than 0.45 times the mass of the sun, the composition of such a white dwarf will be a helium white dwarf. Unless the original core had a mass larger than 0.45 solar mass, helium would not have burnt into carbon. In a similar progression between 0.45 to 1.25 solar mass, you get what is called a carbon oxygen white dwarf, and between 1.25 to 1.4 solar mass, you get oxygen and magnesium white dwarfs. And above 1.4 solar mass, there are no white dwarfs anyway, because you have reached the Chandrasekhar limit. Now, this Chandrasekhar mass limit, which you have derived on the basis of support due to degeneracy pressure alone, in reality requires some corrections. First is the effect of general relativity. We have used the Newtonian form of the hydrostatic equilibrium equation to derive the Chandrasekhar mass limit. In general relativity, you have these extra terms which we had dropped. If you keep them, there is a small correction that appears. And now, in the white dwarf, material is highly dense. So, there are, other than degeneracy pressure, there are Coulomb interactions and other many body interactions that happen within these particles. So, those also cause some correction to the pressure density relation, and these Coulomb interactions need to be included in the equilibrium equation to give you more realistic structures. The star may be rotating. So, in case of rotation, the rotational forces have to be included in the hydrostatic equilibrium equation, and so will be magnetic fields if they happen to be strong enough. Just quick introduction to what happens if you include some of these effects. The inclusion of general relativity, which is shown here using the blue line, and the previous equilibrium equation we showed using the red line. The inclusion of general relativity reduces the maximum mass by about 1.4%. So, it is actually a very small deviation, and most of the discussion that we did using the Newtonian form of the hydrostatic equilibrium equation actually goes through for white dwarfs. The Coulomb corrections come because of the deviation of positive charge distribution from uniformity, because they are located in a sort of arranged manner. We then can compute the effects of that using the standard Wigner site cell technique like in condensed matter physics. And the division of electron charge distribution from uniformity, that can also be calculated, effect of that using the Thomas Fermi correction. So, those two corrections put together, you have a correction term to pressure like this, where x is again P f by m c. And since this is negative, this actually lowers the pressure from the standard Fermi value, and the amount of lowering depends on composition, which is shown in this diagram for different elemental compositions, iron, magnesium, carbon, helium and so on. The vertical axis is pressure in units of uncorrected Fermi pressure, and you can see that at high densities you do have a significant amount of correction. And in the mass radius relation, these then manifest this way. You have the pure Fermi degeneracy pressure equilibrium given by this outer line, and different compositions including these corrections will give you these other mass radius relations. And as you can see, because of these corrections, the upper mass limit can be significantly reduced compared to this 1.4 solar mass if the composition is of a heavy material. If the configuration is supported by rotation and magnetic field, then the shape becomes non-spherical. In case of rotation, the structure equations need to be supplemented with equations like these, and if it is supported by magnetic field, then another set of equations need to be included, which are indicated here, and there is a virial condition where the sum of these energies will go to 0. That needs to be satisfied, and one can solve for these configurations, and you will get a different mass radius relation. What is illustrated here is the mass radius relation for white dwarfs with strong magnetic field in them, and each of these lines correspond to different central magnetic field strengths. This line is for very low magnetic field strength, and this is our original mass radius relation that we have talked about with Fermi degenerate gas. And as you magnetize the star more and more, the mass radius relation begins to diverge from this original mass radius relation. With extremely strong magnetic fields, one can support in principle masses up to about 1.9 solar mass. This is radius, this is mass, and this is the highest values of mass that you can support using poloidal magnetic fields.